Okay. Hey, you guys, how are we doing on the mic? Is it working now?
It's coming.
Still coming. Good. You're good. I'm good? All right, great. Hey, welcome. We're here to talk about technology in terms of what's next, and we're going to explore some really cool technologies, and it turns out that this revolves around salt. And so we're going to be talking about the future technology, and the first one we're covering, Carlos Riva of Poseidon Water, is going to talk to us about building the largest desalination plant in the United States. So Carlos, please come on up and share with us what you're up to in California.
Thank you very much, and good afternoon. As Jim said, this is about salt, but I'm the water guy. And it's interesting, the theme about can technology save us, because I would posit that we need saving in the water sector for the reasons up here. I mean, first of all, you got to understand that all of the readily accessible water on the planet, fresh water, is already spoken for. So we have to look beyond the existing resources. And at the same time, because of the growth in water consumption, every 20 years is doubling. And that's twice the rate of population growth. So that's, you know, an incredibly important factor in terms of the challenges. World Health Organization predicts that by 2050, some almost 4 billion people will be living under severe water stress. Today, they say there are about 2 billion people that don't have access to adequate water, either fresh water or sanitation. And recently, a UBS report came out quoting that the World Economic Forum recognized water scarcity as the #1 risk to our planet, and the implications are vast from that, not only economic but social. In the US, I mean, this isn't just a third world phenomenon, but in the US, we've suffered from a long period of chronic underinvestment in water infrastructure. So that's why in LA, pipes are bursting with rather spectacular effect, because those pipes are at least 100 years old in some cases, and we're replacing them at a rate of a 70-year cycle. So big problems there. And then, of course, people know about the California drought, which is in its 4th year now. Over half the state is in either extreme or exceptional drought. And it's finally, I think, started to sink into the consciousness that something needs to be done. So moving forward, there's no magic bullet here. A number of different things need to be done to address the water issue. First of all, conservation. Now in California, there's been a mandated reduction in water use, which has been successful in the short term, but they conserve a lot in California. And conservation is not just about taking 2 showers a week. It's about investment in the infrastructure that allows you to use less water and maintain the same level of lifestyle. Water recycling is going to be part of that, and water reuse. Reuse, it used to be called toilet to tap. People don't like that phrase, but it means taking wastewater and cleaning it up to the point where it can be put into the drinking water system. That already is done in Orange County. It's going to happen in San Diego County and in places in Texas and elsewhere. Very important. We also need more infrastructure, but we also need new supplies of water. And that's where seawater desalination comes in. We may be the blue planet, the water planet, but 97% of that water is ocean water, salt water. Of the remaining 3%, only 1% is that accessible water that I spoke about is already spoken for. So this was recognized a while back by President JFK in 1962. He said, if we could produce fresh water from salt water at a low cost, that would indeed be a great service to humanity and would dwarf any other scientific achievement. That was 1962, when actually reverse osmosis desalination first was developed in San Diego. It languished in the US. It was done at small scale, but really moved overseas to start to become utility scale. So seawater desal is today a very important factor of the water supply of places like Israel, where it's, I think it's some new plants coming online where it's going to be over 50% of their water supply. in Australia, in Spain, Algeria, Cyprus, a lot of different places that have, are more populated than their local water resources would otherwise allow them to be. So the technology is pretty well developed. It's not fully developed, but it's well developed, very reliable at industrial scale and municipal scale, and has some great benefits. I mean, the first is the whole issue of reliability, and part of that is that it's drought-proof. It's not reliant on rain or snowpack or any of that, and that's critical. The other element is that it's locally controlled. I mean, for areas that import a lot of water, there's always the worry that if there's sort of a regional problem of water, that the party that controls that water, that sends you that water, may not give you the allocations that you need. And so there's a premium placed on having that water under your local control. And for seaside communities, that's something that desalination gives. In California, there's a seismic issue. These large pipes and aqueducts that bring water from the Sierras or from the Colorado River pass through a number of faults, and there could be disruption to that, which could be anywhere from very annoying to catastrophic. And then the water quality is very good. So that's why I think desalination has a major role to play. In the technology that we use is called reverse osmosis, and I'll talk a little bit about that. But it's important that this is a scalable technology. They're units that can be expanded to the degree that you need or made smaller. The real constraining factor here tends to be the ability to deliver the water and how much, really the civil engineering aspects of it, and a lot of scope for continued technology innovation. Let me show you a schematic of what a typical plant looks like. Now, I said that a lot of this is about civil engineering, and it's about getting the water, the source water, moving it around through your system, and then discharging it back to the ocean. And then there's a process component, which is the desalination facility itself. So in our case, what we try to do is to locate our project adjacent to where water is already being used from the sea. And currently, in a number of places, seawater is being used to cool thermal generating plants. So in this case, this on the left is a generator that draws cooling water, 300 million gallons a day, passes through its condensers, and then discharges it out. We take a stream of 100 million after it's already been used and put it into our desal plant. We produce 50 million gallons a day, and then the salt that was in that 50 is it winds up in the balance of the 50, and that goes back to merge with the other stream, be diluted, and then put out to sea. So in a sense, under this configuration, it's a very low environmental impact from the desal plant. Let me go a little further. This is a schematic of the plant. On the upper left are the pre-filters, where you take out all the organics and shells and sand and all the rest of it that come in with ocean water. And this is very conventional. This is what all water treatment plants have, some version of this. It flows from there to the left, which is a microfiltration type of area where you take out everything else but the salt in the water, and then you have a high-quality, highly purified saline that goes into the reverse osmosis area. I should make one other important point, that because you have a high pressure of about 1,000 pounds per square inch and then an atmospheric pressure side, it's very important to capture that energy in the high pressure stream and then use that to repressurize the water that's coming in. And that's been one of the innovations that's really driven down the energy cost of desalination over the last 10 years. Here's a picture of what one of these desalination or reverse osmosis units looks like. There are some 14,000 of these in a system. So you see, this is a lot about plumbing, but there's also a lot of really good science in here. Speaking of technology, how's technology going to save us? Again, these units are number of them operating very successfully overseas, but they're not the end all of this. There's a lot of work going on in terms of trying to find new ways to reduce the energy use. In fact, in our projects, we actually have a prediction in our financial model that there's a significant improvement over the life cycle of energy reduction. Renewable energy is also going to be a factor. We'll have some on site, but possibly looking to procure the majority of the energy from elsewhere. And different controls, new membranes, nanotechnology, graphene, things of that sort, and new pretreatments. But one of the big challenges is that this is a very fragmented market in the United States. There's over 50,000 water agencies, municipal water agencies. Maybe you live in towns that have the water department. It's very difficult for those agencies to innovate at this scale. And this is where I think there's enormous opportunity for the private sector to come in public-private partnerships. So that's really what my company does. We develop large-scale water infrastructure in public-private partnership with these municipalities. We take the risk of development, permitting, construction, and operation, and they take the market risk. That is, we produce the water according to certain standards and a certain price, and then they have to buy it from us. And that's the grand bargain. So the first one is this project in Carlsbad. This is a very important project because this will be the largest seawater desalination project in the country. It's north of San Diego. It'll produce 54 million gallons a day, which is about 10%, 8 to 10% of the water used by San Diego. So it makes a big difference, particularly in a drought. I can tell you, though, this was not built in the response to this drought because it took us about 12 years of planning and 3 years of construction, and my timing was lucky. But nevertheless, it's an important factor. And there was obviously a lot of debate and challenge at the time that we were putting all this together. That's what it looks like. This is the photograph of the schematic I showed you earlier. This power plant will ultimately be taken down, and what will result will be a very low-impact desalination project, which is in the yellow circle there. And those oil tanks are also gone now. So implications. This is the first significant incremental supply of new water in California. Very important. And I think it has the effect of validating this model for desalination at large scale in the US. I think it also validates the public-private partnership model. We get a number of visitors from all over the country and the world that come, and they want to see the plant. And the next thing they want to do is they spend the morning at the plant, they spend the afternoon talking to our municipal partner to say, what's it like dealing with the private sector? Because unlike other industries, this just hasn't happened in water in the United States before, not to any extent. But it's a very attractive model for these, because these municipalities have very significant needs for capital for things like pipe replacement, things that they do well, things that they need to do. And so I think that there's a lot of attention on this model, and I think it also serves to alleviate some of the concerns that have been expressed about desalination. And I can tell you, last week the project was producing water. It's not yet commercial because it's still in the debugging and shakeout mode, but we expect in September it's going to start its testing, and then be completed sometime, thereafter, October, November, but ahead of schedule and on budget, which has been very important. Let me just say a couple of things about the myths of desalination. One, that it's very expensive. Yes, it is more expensive than taking water from a lake or a river. If you can get that, do it, but you don't have those options. That water is gone, it's spoken for, people will fight wars over it, but that's not available. But this is actually a very competitive option against the other incremental alternatives. And in the case of the project in Carlsbad, it sold over a 30-year period to the Water Authority. At the end, they get the facility for $1, but the life cycle cost is lower than their costs of importing over time. Initially more expensive, but over time those lines crossed. Marine life impacts have been a big issue in terms of the permitting. We're not talking about marine mammals, we're not talking about fish, we're not even talking about tiny fish. We're talking about fish larvae and fish eggs. And again, what we're talking about is something on the order of about 2 to 4 of these microscopic fish eggs or larvae per 1,000 gallons of water produced. So we believe it's a very small impact. We do a lot to try to eliminate or minimize that impact. You can't do it all the way, but then you can mitigate by having compensatory projects. So we're developing restoring some 66 acres of new wetlands in San Diego harbor, or bay rather, which will put it into intertidal wetlands, and that's generative of marine life to more than compensate for this. People are concerned about brine. That's a very manageable technical problem and issue to face. So in our case, we're discharged with about a 20% increase in the salinity into the surf zone, and within an area the size of a couple of tennis courts, the incremental increase in salinity is not measurable. This is not an issue, and again, the operation of Carlsbad, I think, will validate that. And finally, electricity use. And I've one more slide on this. People are worried about electricity use, but I think that you've got to look at it in the context of what else you use electricity for. To generate enough, all of the needs of an average household in California using desal water would take 7.6 kilowatt hours. Compare that to heating water, to driving an electric car, to a data server, which is my favorite, and then to air conditioning. You have to make priorities about the use of your resources. And I think what we're trying to do here is take a very abundant resource, which is salt water, to create a precious resource, which is fresh water, and to the extent that we can use renewables and other things, I think that's other energy sources to achieve that, I think that's a real win-win. But I would posit that water is the only ones on this list that are necessary for life. Data centers, very valuable, but you probably don't need, your kids' Facebook pages stored from, well in their past. Okay. Again, what does all this mean? I think there's going to be several more projects built in California. We're certainly developing several more. The permitting regime is going to be very rigorous. I don't care if there's a drought. There will not be any shortcuts, but the path forward has been pretty much set by Carlsbad now. And then I think elsewhere, not only in the States, but other areas that have similar climates will be looking to embrace this technology. So I'll finish up by just saying that, maybe at some point in the future, we may be able to enjoy the desalinated water, for the precious and valuable resource that it is. Thank you.
Okay, so we're going to go through a slight technical change and get ready for our next session. As they say in the West, whiskey is for drinking, but water is for fighting. So I think you're touching on some of these really key issues. So our next speaker, Adam Lowe of Facta Marte, is going to come on up, and he's going to talk about extend this desalination kind of concept further. Where might that lead? And so I think we're really excited about hearing this. And
at 8:30 this morning, if any of you were here, one or two were, I spoke about very practical things that we're doing in Madrid to try to preserve cultural heritage under threat. Yesterday, in the very brief introduction, I started by saying Facta Marte was really a playground for artists, if any of you remember. But basically, what I'm going to do now is to show how we think through things in the playground. So where do ideas come from? How do you apply them? What do you do with them? Do you just think blue sky thoughts and then do nothing? Well, one of the projects that we began about 5 years ago was a project with a group of geologists, a group of philosophers, a group of historians, particularly historians of cartography. The project is a project to say that the Holocene era, that's the geological time frame we live in now, is coming to an end. And the Anthropocene epoch is likely to begin. Well, the geologists have been negotiating this for the last long time. And geologists move almost as slowly as geological time. So it's not a rapid or lightly conceived decision. But mainly a geologist called Jan Zaleski has been arguing that humans are now the largest single force influencing geology. So not climate change, it's not a climate change argument at all. It's an argument about geological change. So with that in mind, what I'm going to try and do, and I feel on slightly thin ice because a lot of things that I'm going to introduce now are very much thoughts and ideas rather than concrete realities. But basically, we start thinking about buildings because I was in Rome and I was looking at the Pantheon. And here you have the largest unreinforced concrete building, begun in 30 BC and finished in about 100 BC. So it's a concrete structure with no reinforcing. Concrete is a material I love. So I'll come to that in just a second. I started wandering around Rome thinking there must be more of these amazing ceilings. And there are. So this is a smaller one, less well known than the Pantheon. But it's also the ceiling of San Bernardo alla Terme, so it's by the baths. And it's a second unreinforced concrete ceiling from, this one's probably from the 2nd century AD. But this has been standing there for a colossal amount of time, nearly 2,000 years. It's in great condition. So while I was in Egypt working, there are obviously building materials for different places. So concrete was invented in Rome not by accident, but because all of the materials you need are there in the city. So that's why the Romans got concrete. They very cleverly worked out how to cook it, how to heat it up, how to do all the things you need to make concrete set. In Egypt, the dominant building material was mud brick. And this is a 7th century mud brick town, which is been deserted for a long time. It's still in remarkable condition. So mud brick's good as long as it doesn't rain too much. Okay, so the question of how you structure things. So I really should have here a picture of Grand Central Station or of Boston Public Library, but Guastavino was a Spanish architect who came here in the 1880s, and he started building vaulting. So it's built on the principles of mud brick architecture, but you can build vast vaults without having to build an infrastructure first. So that's the importance of the timbral vaults that Guastavino vaulting is based on. The next thought was sort of about decay. So in England, because we're rather romantic and because we have a complex relationship with the past, where actually we really rather like it decaying. So this is the Bank of England that was built by Sir John Soane, the great architect of the 18th century in England and early 19th. But he commissioned Gandhi to basically conceive his greatest building as a ruin. Okay. So this was done contemporary with the building being built. And the point of this is that buildings now are not built to last very long. So when you're working, and we have to do this quite a lot with some of the material things, when you're working, if a building lasts 50 years now, that's probably more than its spec. So buildings are becoming thought of, I mean, in a way, as a commercial entity, that with the population expanding at the rate it is, you build a building now of 20 stories, but in 50 years' time, they'll let you build 100. Therefore, it's cheaper to knock the building down. So actually, we don't need the buildings to last as long. So that's a little preamble. Now you're going to get 3 or 4 preambles before we get to the punchline. The second preamble concerns lava. Actually, lava is fabulous because it gave the pozzolanic ash that the Romans needed to build the concrete. But I'd always wanted, in a rather childish way, to make lava. And then, of course, you find that people have already done it. So everything you think you want to do that's a clever thought has almost always been done already. And I discovered there's a terrible typo on this slide because it should say 1790, not 1970. I apologize for my staff. But James Hall was just the great Scottish experimental geologist. I mean, what a great idea. That's a job I want, to be an experimental geologist. And so in Edinburgh, he got a couple of forges to heat up the raw materials to make basalt up to about 1800 degrees. They had a couple of major explosions, some very major fires. But he cast lava in the 18th century in Scotland to prove Hutton's theory of geological formations. And he then went one stage further, which is not the subject of this talk, but he simulated tsunami to demonstrate that the boulders above Edinburgh were thrown there by a vast tsunami, which he did as a model. And those are the sort of things that I love. So actually, I love the 18th century and the early 19th century when people were full of curiosity. And this is really a talk about curiosity. So Carlos is the doer. And in this context, which I think is absolutely amazing what he's doing. But in this case, it's really about curiosity. Can we rethink how to do something? So in Madrid, we set about trying to do what James Hall did. And I won't let this run for very long, but if you've never been in a foundry, what we're doing here is profoundly dangerous and very exciting. And it's one of the reasons everyone's been asking me why I live in Madrid. One of the reasons I live in Madrid is you can do things like this without health and safety coming round all the time. They come round quite a lot. But basically, there we cast blocks of lava. We've now cast quite big blocks of lava. And what we do is we'll now go around trying to persuade artists that they really want to cast in lava, and then I can pay for doing more research. So this is actually, if you like, a leader for a job. The other thing that was going, so preamble number 3 just started, but it's related to lava. So if you think of that first image of lava, a thick, viscous material, printing concrete. So now the big growth industry that everyone talks about is 3D printing. We've now built, so this was the first prototype concrete printer. It basically moves along and it works like a colon. It pumps out concrete. Not an attractive image, but that's how it works. And we can then start to control what it does with the stuff it's pumping out. So let's see if I can do this. Is it not going to let me do it before there? So after a little bit of experimentation, we can start to do a lot of things with that pumped concrete. So we can pump concrete that does look a bit colonic. We can pump it that looks a bit like spaghetti. We can pleat it and fold it. We can watch how it breaks and reforms. And all of this is dependent on the concrete mix. So it's dependent, it's a bit like cooking. So basically, Factum's workshops are remarkably like a good kitchen, where you try lots of different ingredients and you see what they do. Bit by bit, we were able to print structures that were up to 4 meters high. This was about 4 years ago. We've now got a concrete printer that prints 7 by 5 by 5 meters. So we're getting near building size. And this is starting to be very interesting to a large number of architects who are rethinking how buildings are going to be built in the future. I will get to salt, Carlos, I promise, in a minute. So the whole way of rethinking how you build becomes one of the subjects. This is Grabazione Colla in Zurich, building buildings with quadcopters that are positioned, so they'll fly and computer deposit the bricks. So this is entirely built from a computer program. I'll go past these ones. We talk to people like the domains here in MIT, because one of the big subjects here that's received a lot of support from the building industry is origami, because basically most buildings are flat pack buildings, sheets of glass, sheets of steel, but how you fold building materials becomes a really interesting topic. So Eric Domain is one of the geniuses of the new field of origami that's being applied to building. One of the ones I like, this is a project done by a student when he was at the Royal College of Art, called Marcus Kayser, who was using only the sun focused through a lens to melt sand. So he was doing printing in sand in the desert. So it's effectively 3D printing only using the sun and a CNC and a machine to position the lens. So you're actually literally doing what you did or what I did as a child with a magnifying glass, that magnified, and you can heat the sand to a point where it fuses. What we do in Madrid is we take to bits microwaves, put them back, wire them in strange, complex ways that, again, health and safety wouldn't like, and build printers to print crystallized sand. But the problem we're having there is they're not strong enough. So the sand is still very brittle. But we study natural form, often through the history of science. We study termites. They are amazing builders. And this is a project by a man called Rupert Saw in Namibia. So termites' nests are always built at a slight angle, and I'm not going to go into this at length, but the reason, according to Rupert Saw, is the termites need to get oxygen down into the bottom of the termite's nest. So they set up a vibration as the wind goes over the top that means the whole nest acts like a pair of lungs, and it's sucking and expelling oxygen. And that's extraordinary. So think back to those little octocopters building the tower. These are the ants, and they're doing it collectively, and no one of them knows what they're doing, but all together they know. Now this bit I'll go through very fast. I said I was working with the geologists, and we were trying to rethink the Earth. We were trying to think of a monument for the Anthropocene. And so one of my loves is cartographic history, and I found this absolutely amazing map, which I think is the first map of the surface of the Earth without any water. Obviously, it was done as they were trying to prove the truth of the Bible, and they were looking at the flood, and this was the state of the Earth before the flood. So it's from a book by Willem Godde, published in Utrecht in 1700, and it shows what the world looks like without any water. We then started thinking about, how do you project the world? How do you think about it? So bottom right is the world we mainly think about. That's more familiar to us. So this is actually the same as the Gorey. It's a depth map. So the darkest areas are depth, and the whitest areas are height. And here we go through different projections. So if you think about using an equirectangular projection with north at the top, that's what we've all been brought up believing the world looks like. We know it's a globe, but when you flatten it and put it on a rectangle, that's what it looks like. Or Buckminster Fuller proposed the Dymaxion projection above. The first image of America on a map is a cordiform projection, which is basically the Waldseemüller map, which is now here in the Library of Congress. And if we sacrifice the rectangle, we can make it look like the azimuthal projection above. But in Factum, we're working on trying to say perhaps the most radical thing we could do is change the way we think about the world. So this is a land-centric projection where we're sacrificing water top and bottom, not Antarctica that comes over on the right or the North Pole that comes in the middle. And I think this could be the projection that actually articulates the world we live on now, where water is a big issue. So I'm going to jump, well, what we've been, come on, let me jump that. There, okay. So what we've been doing is we've been actually building models of this and then flooding them. is a project we're proposing for Venice. I mean, Venice is the place where the relationship between sinking land and rising water is perhaps most vulnerable. So we want to build a relief model of the Earth and then flood it. But when I proposed it in 2012 to a group of climate change specialists, they immediately broke down into argument about whether the sea levels were going to rise 1 centimetre in 10 years or 5 centimetres in 5 years. And I kept saying, but that's not the point. We're trying to rethink an idea. We're not, at this stage, trying to do hard science. Hard science will follow, but ideas and hard science are always in balance. So this is where we come to salt. So I'm going to try and wrap up very fast. This is probably quite hard to recognize, but it's a relief map of the north of Egypt. If I add some sea level, or approximate sea level, it looks a bit like that. So the blue area is up to 130 meters below sea level. It's known as the Qattara Depression. Just for the sake of argument, Alexandria is at the top of the delta, but look how flat the delta is. So the Nile Delta at the moment is in very big trouble because the Aswan Dam has stopped the silt flowing down. And the Aswan Dam has stopped the silt flowing down. So the Nile Delta is not rebuilding itself, and the Mediterranean is rising slowly. So the delta in the Egypt is now within 5 centimeters of becoming brackish, becoming salt saline. That would be a crisis. So thinking about that vast area of the Qattara Depression, which is up to 130 meters below sea level, the what if, and this is probably where I'm going to stop, otherwise I'll go on too long. The what if is, if we can bring in the Mediterranean, 55 kilometers from the Mediterranean to the Qattara Depression, if we can drop the water 30 meters, vast amounts of water, you can produce an extraordinary amount of hydroelectricity. You can take the hydroelectricity off into evaporation tanks, because it's one of the hottest places on the Earth. You use a small amount of the hydroelectricity to add heat to the water. You evaporate it up to the top of the cliffs and run it back down to the Mediterranean, irrigating the whole area between the Qattara Depression and the north coast. Now, one of the things I like is climate changes all the time. So within historical memory, we know that the area between the Qattara Depression and the Mediterranean was the breadbasket of Europe, because Pliny tells us it was. So what we're looking at here is a shift of climate, which isn't necessarily human. So we put this fresh water back. We're left with 3% of the water as salt. So the slag heaps that we would create are going to make this look like a little molehill. But really, the what if now is, can we turn salt into the building material to replace concrete? So suddenly, if we can, we have an absolutely wonderful model for the monument of the Anthropocene, which only has positive effects. We can go into it in more length, even for the wildlife in the Qattara Depression. So that becomes a whole other subject. But the work we're working on, first of all, was to cast salt, to work on how to actually mix salt with sand and heat it up. Myself and all the foundries started vomiting because it was giving off chlorides that weren't very healthy. So we've temporarily backed off on doing the sand and salt mix. But then in one of those wonderful moments, there are new products to make your shoes waterproof based on silicates. And if we can coat the cast salt and make it not melt for 50 years in Connecticut, would people build with salt? And would that perhaps help Carlos not put any salt back into the ocean, but only make beautiful water for people to drink? Thank you.
So I think that's a pretty dramatic take on what to do with salt. Thank you very much, Adam. And thank you, Carlos, for really bringing water to California. So we have a chance for a few minutes of questions, and I'd love to hear from the audience. What are you guys wondering about, either about the biggest desal plant in the country or about a possible future of remaking northern Egypt into a garden breadbasket for Europe again? Yes?
What is the insulative quality of salt?
It depends what you do with it. So there's a group on the West Coast who've been using salt to print with by mixing it with certain kinds of glue. So they've been building 3D printers based on salt. The insulation qualities depend on what you do with your structure. So actually, if we could mix salt with aerogel, aerogel is the lightest known silicate, which has the highest insulation properties in the world, then you could really have something extraordinary. Aerogel was designed to put on the nose cones of shuttles, and is 98% air held within a silicate sponge.
Great, yes.
How much power does the power plant need?
It needs about 33 megawatts, more or less, for that unit. And again, it's a big user. But one of the things that's also very interesting about it is that we're a very attractive user of electricity because it's very easy for the utilities. We can accept backing us down during peak periods of use because we can store water and we don't always have to be producing at that or consuming at that level. So it's an interesting way for the water world to integrate with the electric power world as a means of stabilizing some of the fluctuations in electric power demand. There's a lot of talk now about the water power nexus, you know, in the utility business, and desalination can be an important factor of that.
Wow, cool. Yes.
Technology change is always brought along with it, for good and for bad. Cultural change, the type of massive scale rethinking of how we approach technology and problems like this. As you're thinking those through, what do you do in terms of trying to anticipate and plan for, and I'm not sure it can be planned for, the type of cultural change that comes along with this that could be at the same massive scale as the engineering change you're making?
There are sort of various levels of answer to that question, I think. So I don't want to make us sound irresponsible, but I think the work we've been doing on this kind of thing is what I would think of blue sky thinking. And of course, we look at the situation from many angles. So it begins with the Aswan Dam and the silt and the delta and the question of what it would take to build a canal 55 kilometers, how much electricity you generate, all of those things. So you're looking at a large number of different variables. But really, I think the main purpose of the work we've been carrying out is to say, we know the Mediterranean, which is marginally more salty than other oceans, because the Mediterranean basically is a basin. It has water coming in. It has no exit. I mean, it has the Straits of Gibraltar that sort of change a little bit, but the pollution levels in the Mediterranean are going up. The height of it's going up. Everyone's short of water in that region. So there's an obvious thing, which I think Carlos articulated very nicely. Since the 60s, people have been saying desalination has to happen. To me, it's a mystery that it hasn't happened more already. I mean, really a mystery. Because actually, the change, the amount of energy required, I thought your visual was very, very good. But it shows relative to other electricity uses that it's not vast. So actually, why aren't we thinking much more radically about how to extract water from this great reserve, remove the salt, put it back in the ocean? But if this got onto a great level, putting back into the ocean obviously is finite. But if we can replace concrete, which is one of the largest contributors to global warming, the production and use of concrete, this would have a radical effect on many levels. And really, it's still an idea. So the idea, what I presented today, is an idea that we've done a lot of physical tests on. So I have got salt, so it doesn't dissolve for about a month. But I haven't got it yet, so it doesn't dissolve for 40 years. But that would have to be accelerated testing. So, and really that's where we would hand over to other people, because really I'm not interested in running the building industry. I am interested in generating ideas and saying, what can a group of people who are thinking freely actually do to contribute to exactly what your question's aiming at?
Well, and I think your framing of the Anthropocene, I mean, that's geology being remade by human beings. And so you picked a pretty bold example of what that might look like. Yes, the lady there, please. Yes. And please say your name if you have a chance. That would be great.
I'm Anne-Marie Foss, and I believe about more than 70% of water consumption is for agriculture. Can you conceive of a time where the cost can come down of desal so that it can be addressed to that percentage of water usage? And what would be the biggest impediment to getting that cost down?
Well, I don't think that, frankly, that the question should just be, how do you bring the cost down to continue agriculture as we know it now in the West? Because there are two things that have to happen. One is that I think agriculture has to change. Again, Israel is the great example where they have adapted an agriculture to the realities of their water supply. Desal's been part of it, and they work in tandem. In California, agriculture was developed on the basis of incredibly inexpensive water. And so it's resulted in practices that are probably not sustainable in terms of agricultural techniques and the crops that are grown. So to answer your question, I think the costs will come down over time. Again, I don't see them ever being as cheap as just tapping into a lake or sucking up the groundwater, but that's not an option. But they'll come down over time, and I think the unit cost of water used for unit of production of agriculture will have to increase because people will have to invest in new forms of agricultural technology.
Yeah, like drip irrigation. Yes.
There's a whole, is this working?
Yeah.
There's a whole food chain, you know, marine life and the little shells and sand that get sucked in and the little fish that get sucked up to the filters and the fish that feed on those little fish. When you talk about a cultural change on land, but what about the whole food chain and the disruption to, you know, the things that eat the things that eat, you know, and you're sucking that in. And the little fish are getting pulled up to the filter, and something's happening to them, and something's used to eating
Well,
them.
and I just have to say, being from California, what we do in terms of piping water from Northern California to Southern California kills far more, you know, of the fish wildlife than this will actually have to seize.
It's very interesting. Yeah. Speaking of electricity use, the amount of electricity that it takes to force the saline water through the reverse osmosis filters per unit volume produced is approximately the same that's used to pump water from the Sierras to San Diego.
Yeah.
But in terms of the marine life, it's estimated, and again, this is by independent studies that have been done by oceanographers, marine biologists and the like, that for a plant of 50 million gallons, again, depending on where you draw your source water from, it's something like 80 million fish larvae and fish eggs a year. Now, that's a big number, but when you consider what that means in terms of what's the real impact of that, it's minimal, because again, an adult fish will release hundreds of thousands of eggs and larvae into the world, and so into the ocean. So if that is the sacrifice, and then you've mitigated by producing that much through restoring wetlands, your net effect is very minimal. And I think that this is one of the regulatory issues that's very complicated, in that in California there are a lot of different agencies that are looking at that, but it's hard to get someone to focus from a holistic level. So if you really said, okay, we have this marine life for this unit of water, the marine life impact, but by the same token, if we're taking from highly stressed areas in the Sierras and these streams that are drying and fish species going extinct, and you're having that impact with the status quo, shouldn't we be doing something different and judge desal impacts against the status quo, not about, you know, worrying about the impacts on you know, some anchovy larvae?
Yes, in the front here.
Funded Poseidon, and how many years did it take from conception to finality?
Well, it was about 12 years of permitting, cost about, it embarrasses me to say, but over $70 million to permit. And then construction was started 3 years ago and is just concluding now, and it was about $1 billion project, was financed by equity pension funds and bonds that we sold in the market.
The private sector.
Yes, private sector.
Yes,
Yeah,
Fran.
you talked about the concrete was the largest contributor to global warming. Are you talking about the thermal footprint that it leaves on the landscape?
Yes. Yes, in the back, the lady in white, yes.
Lady in white.
Hi, Deborah McQuinney. What is the shortest amount of time that you can envision a water desalination plant being built? I mean, just shortest amount of time.
I would have to say, you have to ask the question where, because I think in California, the permitting regime is quite challenging, and there's a lot of study that needs to be done to support it. So you have to go and collect data. So I would think permitting would probably take you, I'm going to throw out 5 years. It took us 12, but you know, we've kind of been pioneers in that regard. But let's say 4 to 5 years, and then to build it, you know, less than 3 years. So it's not something that happens overnight. It's not something that you do in response to a drought. It's something that has to be a conscious decision to incorporate some of this new type of supply into a revised sort of assortment of different supply options that you have.
So we're time to wrap up, but we'll take one last question and then I'll give a close. So please.
Is the environmental impact on the fish the main thing that makes it take so long to get permitted? And also, are there any technologies being developed that could minimize that aspect of it?
Yes well, I'm not sure whether there's a single reason why it takes so long. I mean, that's part of it. But there's energy use. It's just, California is a very challenging place to permit anything. But I think there are some technologies that are being considered, such as drilling wells, so you go underneath the seabed in order to do that. We've actually just spent the last 2 years on a different project looking at a whole range of different intake structures, realizing there's one already there and existing, but the regulators asked us to look at all these different types of seabed infiltration galleries and pipes that are like drains that go under the seabed. They all have their challenges. A number of them are not feasible in the open coast, and ones that are more expensive than the facility themselves and take a long time to build. So I think in certain niche areas it'll be possible, but the jury's out on just how to do it. Our view is that you can also go and take these aren't just open intakes. There are things that you can do to screen, fine mesh, and the like to minimize any impacts.
So I think that, you know, we've heard the compelling case that scarcity of water has a major impact on the future of humanity, on people able to live in arid environments like my home state, California. And so I want to basically have you all join me in thanking our two speakers for exploring this about what's next. So thank you very much. Thank you. That went well. That went well. Thank you.